In recent videos, I have been talking about the amazing and complex geology of the Cache La Poudre Canyon north and west of Fort Collins, Colorado, and its river that runs through town here, and the rocks that are able to be collected. The canyon is rich in mafic and ultramafic, igneous and metamorphic rocks, and the minerals pyroxene and magnetite are fairly abundant, and there are some amazing occurrences of these minerals, as we will see in this video and as we saw in the previous video about magnetite. I hope you will stick with me as we look at some of these unique occurrences and talk about how the Bowen's reaction series comes into play with many of the striking and contrasting patterns that we come across as we study the different kinds of rocks that can be found in this area. Here I am mixing some magnetite sand with some plain beach sand in order to represent a body of magma. I can easily separate these out again with a magnet, so I'm not wasting my sand. So let's mix them up pretty good. So in a melt, we have all different minerals, different elements, just as atoms floating around in this melt. And as crystals begin to form, according to the Bowen's reaction series, olivine, I believe, is one of the first to crystallize out, and it works its way up, with quartz being one of the last. And we looked at some magnetite that made these eye shapes in the rock. You might remember these two specimens from our recent video about magnetite, where the crystals separated out the iron and related elements from the material immediately surrounding them, therefore creating this unique pattern. This one here is actually a mica schist, lots of biotite mica, and then the second specimen is more of a granitic rock with basically that salt and pepper pattern you might imagine in a plutonic igneous rock. This represents a nucleus of a magnetite crystal. So it's in that magma, and it pulls all the iron out of the magma just surrounding it. Okay, and there you can clearly see one of those eyes we were looking at. Now let's do the same thing with another smaller magnet. Same thing. You end up with, now we've got two eyes. Okay, so when there are few crystals scattered in the magma, we can end up with this appearance. But more commonly what happens is there are plenty of nuclei, and these nuclei draw out those elements from the magma, and the remaining magma ends up being almost exclusively, for example, in the case of a granodiorite, quartz and feldspar. So the pyroxenes and hornblends and minerals of that nature crystallize out first, and they appear to be floating in a white background. Kind of the opposite. Oh, and that also happens in the rocks. The crystals join together. I didn't mean for that to happen, but it's a good example of what goes on. In my recent video about basalt, we touched on the porphyritic basalts, commonly known as flower stones, and they are a great example of these processes of how the growing crystals can drastically change the nature of the remaining magma. So here are a couple of specimens of granodiorite from the Cache La Poudre River. And you can clearly see here that the darker crystals, most likely pyroxenes or maybe hornblende, crystallized first. You can see that because they appear to be floating, quote unquote, in the white background. And in this example, you can see it even more clear. And here the crystals, it almost has a porphyritic appearance where the little florets of the darker crystals are surrounded by the lighter background again. And again, this goes back to what we're talking about in the Bowen's reaction series, the order of crystallization. Once these darker crystals formed, the remaining magma was a completely new composition. and therefore the extreme difference in color. I've been doing a little bit of research on pyroxene, and evidently there is a significant relationship between pyroxene and iron, especially magnetite and a few other iron minerals. And so that's why I thought it was fitting to mention the magnetite in this video along with the pyroxene. And from what I understand, both are pretty high up on the Bowen's reaction series in terms of crystallizing out of a magma long before other minerals do. They're near the top of the list, if that makes sense. And here we're seeing a couple of examples. This first one is a small piece that I cut and polished years ago that shows the beautiful elongated pyroxene crystals. I always call it dendritic. I'm not sure if that's the correct term. And then here we're looking at a rock that I featured in the video we did of a rock hunt up in the canyon on a high and dry riverbed far above the current river level. And this appears to be a section of a vein, a pegmatite vein of granodiorite. And you can clearly see how the elongated crystals of pyroxene grew first, evidently in from the sides, and then the remaining material cooled around it. This next rock we're looking at has always been interesting to me. I just found this one the other day, but I've got several. And as I have been doing research on the pyroxene group of minerals, I'm finding out that they vary quite a bit, both in hardness and in reactivity in terms of how they react to erosion, which may explain why some of these rocks have only the voids left behind by the crystals, and others, the crystals are still present within the rock. As we said earlier, they are near the top of the Bowen's reaction series in the sense that they crystallize out of a magma first, and the quartz and feldspar are nearly last. And I believe it is this fact that leads to these unique rocks and the extremely well-formed elongated pyroxene crystals we have been seeing, surrounded by a rather uniform light-colored matrix. I sure hope you have found this video enjoyable. If so, please give it a like and share it wherever you can, and by all means subscribe. God bless you guys.